Okay, so now we're going to be discussing about exponential growth and decay models, as well as the specific application with first-order circuit networks, specifically RC and RL networks. So the first application, we have the following form, dx dt equal to some kx, and we're given some kind of initial condition equal to x naught. Now, in this specific situation, this is just an application of first order separable, or a separable differential equation. So as such, if we divide x to both sides and multiply dx, we get dx over x equal to k dx. We integrate both sides to give us the following. ln of x equals to kx plus c. Now, in this specific situation, what we can see is that for t is representing time, must always be greater than 0. So as such, x, the absolute value, can be dropped. So ln of x is equal to kt plus c. Taking the exponential to both sides, we get x of t equals to c e to the kt. From here, we're able to figure out all differential models are modeled by some kind of exponential growth or exponential decay. There's a lot of specific situations, a few including stuff like financial growth or financial decay, talking about bacterial growth, talking about time constant networks or single time constant networks, so on and so forth, are all modeled by this following solution. Now, C is considered the initial value or the starting value of any kind of model, any kind of differential equation model of first order that can be solved by separable. Now, K is called the constant of proportionality. Constant of proportionality. This can be positive, this can be negative, but it cannot be 0, because if in the event it's 0, then the growth remains the same. The solution to it is just a constant. So as such, under the condition that the constant of proportionality is non-zero, it could be positive or negative, the differential equation that models a lot of growth and exponential growth and decay systems is given by this differential equation. Now, a specific situation, or rather two specific situations, are in RC networks. So suppose you have some kind of battery modeled by V. You have R, and you have C. Here in this specific situation, V, the output, is with respect to here. V out of T is equal to some initial times 1 minus e to the t divided by tau, roughly. Now, tau is what's called a time constant. And for this specific network, tau is equal to RC. To describe what a time constant is, it's the value for however long it takes to charge a capacitor up to 63% of its total value, or equivalently, for current to drop down to 37% of its initial value. Now, why these numbers specifically? If we let t equal tau, then we have that 1 minus, or sorry, there's a negative here. 1 minus e to the negative 1 is roughly about 37, is roughly about 63%. If we have just e to the negative 1, that's roughly about 37%. This is for charging, and this is for current. Now, that is as far as we may want to discuss for RC networks, that they can be modeled by an exponential growth, and actually in this case, an exponential decay. The second model is an RL network. So we have a resistor and inductor in series, and we're asked what's the output voltage over here. From here, V out of t is equal to some kind of V1 minus e to the negative t divided by tau. Exactly the same as an RC network, only except tau is different. Tau, instead of being R times C, because there is no capacitor here, is instead L divided by R. L representing the inductance of the inductor, and R the resistance of the resistor. And similarly, this also describes that we have 63% charged and 37% current at t equals tau. And that wraps up first order differential equations. So to summarize, we have a lot of concepts from first order differential equation that we covered in thorough detail, did a few example problems with them, and we showed now the application. We can see that for us electrical engineers, that the most specific case of application is within the concept of single time constant networks, anything that's modeled by RC or RL. Next time, we'll be discussing about higher order, starting first with second order and generalizing it to higher order. Until next time, thank you.